The question that I have is, could you do an example on finding moment by the scalar and vector methods in a 3D problem? We covered the scalar method in another video. I don't want to repeat the details here, but here are the results we got. If you are curious about whether the vector method will lead to the same results, here is the analysis to convince yourself that it does. So I defined my R vector to go from point O to point A, and therefore the component form of the R vector is this, and the component form of the F vector is this, and then we kind of go back to the definition of MO and construct the 3 by 3 determinant and come up with this equation involving the 2 by 2 determinant simplified. And you can easily see that the x component of this MO vector is exactly equal to what we got here by the scalar method, and the y component is exactly same as this, and the z component is exactly same as this. Let's go ahead and do this numerical example. So we have a force here given in its component form, and we want to find the moment of this force about each of the three axes, x-axis, y-axis, and the z-axis. To do this by the scalar method, the first thing you want to do is to draw these arrows representing each of the components of the force, because you need to be able to visualize the components with their proper directions in order to be able to write down the equations for each component with proper values for the perpendicular distances and proper signs. But when you draw these arrows, pay attention to the signs. So here I have a positive component in the x direction, but negative component in the y direction, positive component in the z direction, right? So you want to direct these arrows in the appropriate directions. So you can see I have drawn the 30 Newton in the positive x direction, and 20 Newton in the negative y direction, and 50 Newton in the positive z direction. So here are my calculations, and I'll let you find your own way to convince yourself. But let's go one of them here. Let's say the first one. All right, so we are finding the moment about the x-axis, right? So any force that is parallel to the x-axis will not make a contribution. So 30 Newton is one of those. It's exactly parallel to the x-axis, and therefore you can forget about that. So only the remaining two components, 20 Newton and the 50 Newton, will make a contribution. So let's take 20 Newton, all right? So we need to find the perpendicular distance from the x-axis and the direction, right? So here is the line of action of 20 Newton, and this is the perpendicular distance to that. So perpendicular distance is exactly equal to 2 meters, right? So that's what I have over here. And you can also see that this force is going to be twisting the x-axis in the counterclockwise direction, and that's why I have a positive sign in front of that. Now taking 50 Newton, this is the line of action of that force, right? And the perpendicular to that line of action from the x-axis is this one right there, right? So the distance of this line from here to here is exactly equal to 4 meters. So that's what I have over here. And you can also see about the x-axis, this 50 Newton is going to be twisting the x-axis in the clockwise direction, and therefore I have a negative sign over here. So this is how you deal with each of the forces in the scalar method. So sometimes you can immediately see the perpendicular distance and the direction. Sometimes you have to do some temporary construction lines like I have done over here in order to do this without an error. So I'll let you do these two and convince yourself that these numbers are correct. Alright, so here are the details of the vector method. You can easily follow through, and eventually we get the same results, right? So this is the MO vector. You can see the x component is 160 minus 160, which is exactly the number we got by the scalar method. The y component is 210, and that's what we got over here. And the z component is 180, and that's what we got over here.